Hello, welcome back to Sleep Science. Tonight, we are going to talk about something that has been happening beneath your feet since before life existed on this planet. Something that has never, not once, not for a single second, stopped. Something that is happening right now as you lie there, as your breathing slows, as the room around you gets a little quieter and a little darker. The earth beneath you is on fire, not metaphorically, not in some poetic sense that gets walked back 2 sentences later. Literally, actually, physically on fire. And it has been that way since before the first single-celled organism flickered into existence in a shallow sea somewhere, before the oceans themselves existed, before there was anything to call Earth, except a churning, half-molten ball of rock and metal, still figuring out what it was going to be. And here you are, lying on top of it, completely still. Which is, when you sit with it for a moment, one of the stranger and more quietly beautiful things about being alive on this particular planet. Right now, under wherever you are lying, the crust of the Earth, that thin skin of rock you live your entire life on, is somewhere between 5 and 70 kilometers thick. In the grand scheme of the Earth's total radius, which is about 6,370 kilometers, that is almost nothing. It is like the skin on an apple, less than that in some places. Under the oceans, the crust is sometimes only 5 kilometers thin. 5 kilometers of rock between the ocean floor and the upper mantle. 5 kilometers between all that cold, dark water and something that does not have a name in everyday language. Something that is not quite solid and not quite liquid. Something patient and pressurized and older than almost anything. The ground feels permanent beneath you. That is the thing. It feels like the most stable, fixed, reliable surface in the universe. You press your hand against a wall and it does not move. You stand on concrete and it holds you without any effort at all. Every human building that has ever existed has been built on this thin shell of rock and called it solid ground, called it permanent, called it home. And in a way, it is. In the time scale of a human life, the crust barely moves. Your house will not slide away tonight. The floor will be there in the morning. That is true. But zoom out a little, give it 1,000,000 years, and the floor you are lying on right now has been somewhere else entirely. The plates, the massive sections of crust that the Earth's surface is divided into, are moving. Right now, all the time, at roughly the speed that your fingernails grow. 1 to 2 centimeters per year, depending on which plate you are thinking about. Some faster, some slower. But all of them moving, all of them being pushed and pulled by currents in the mantle below, grinding against each other at their edges, pulling apart at others, one sliding beneath another in a process called subduction that we will come back to because it is where most volcanoes are born. Your fingernails grow about 2 to 3 centimeters per year. That is, more or less, how fast North America is drifting away from Europe right now. There is something quietly funny about that. You are moving. The ground beneath you is moving. The continent you are on is slowly, slowly drifting, and none of it is noticeable to you at all. Not even slightly. The only reason we know is because of GPS measurements so precise they can detect millimeter-level changes in position over months. But it is happening. Always happening. Never not happening. And the reason it is happening, the engine driving all of this continental drift, all of this plate movement, all of these slowly shifting continents and opening ocean basins and rising mountain ranges, is heat. Heat from deep inside the Earth that has been there since the very beginning and has never fully left. Let's go down. Let's go through the layers and see what is actually there. You are lying on the crust, the lithosphere, technically, which includes the crust and the very top part of the mantle, the rigid outer shell. This is the part that is divided into plates. This is the part that moves as a unit. It is rock, mostly, the kinds of rock you see if you go to a cliff face or a quarry, or look at the stones in a riverbed. Granite, basalt, limestone, sandstone. Old rock, familiar rock. Rock that has been shaped by wind and water and time into something that looks and feels like it has been here forever. Below that is the upper mantle. And this is where things start to get strange. The mantle is not magma. That is a common misunderstanding. The mantle is not a vast underground ocean of liquid rock that volcanoes are just punching holes in. It is mostly solid. Mostly. But it is solid in a way that is different from the rock you know. Solid under such extreme pressure and at such extreme temperatures that it behaves over millions of years like a very thick fluid. It flows. Slowly, impossibly slowly, but it flows. In the way that glass, if you had millions of years to watch it, would slowly flow downward. The mantle is like that, a solid that flows. A slow, patient, ancient kind of movement that does not have a good comparison in everyday life. The upper mantle is roughly between 30 and 660 kilometers below the surface. The temperature there ranges from around 500 degrees Celsius at the top to over 900 degrees at the bottom of the upper mantle. Hot enough to melt most metals. Hot enough that the rock itself begins to behave differently, begins to soften and creep and move in ways that the rock near the surface never could. And in this upper mantle, there is a specific layer, a zone between roughly 100 and 350 kilometers down, called the asthenosphere. And the asthenosphere is the key to understanding almost everything about volcanoes and plate tectonics, because this is where the rock is at its weakest and most plastic. The pressure here is still enormous, but it partially balances the heat, and the result is a layer of rock that is ever so slightly softer than the layers above and below it, soft enough to flow in convection currents, warm material rising, cooler material sinking, a slow, endless circulation that drives the movement of everything above it like a very, very slow conveyor belt. The plates are essentially riding on top of this. Below the upper mantle is the lower mantle, which is also solid, but under such enormous pressure that words do not quite capture, that even though it is hotter than the upper mantle, it stays solid because the pressure will not allow it to melt. Down through 660 kilometers to about 2,900 kilometers below the surface, mostly composed of minerals that only exist under those conditions. Minerals that would fall apart into simpler compounds the moment you brought them up to the surface. The lower mantle is deeper than any human technology has ever reached. We know it is there because of seismic waves, the ripples that earthquakes send through the planet. Waves that change speed and direction depending on what material they are passing through. The whole interior of the Earth was mapped, not by drilling, which we cannot do to anywhere near those depths, but by listening. By placing seismographs all over the planet and recording every earthquake and paying close attention to how the waves arrived and what that told us about everything they had passed through on the way. Then the outer core. The outer core begins around 2,900 kilometers down and extends to about 5,100 kilometers. And here, at last, we have something genuinely liquid. The outer core is liquid iron and nickel, an ocean of molten metal at temperatures between about 4,400 and 5,000 degrees Celsius. And this liquid metal is also moving, churning in a slow convection of its own, driven partly by heat from below and partly by the solidification of iron at the boundary with the inner core, which releases heat as it crystallizes. This motion, this churning liquid metal, is what generates the Earth's magnetic field. The magnetic field that deflects solar wind. The magnetic field that makes compasses work. The magnetic field that protects the atmosphere and, by extension, all life on the surface, including you, right now, lying there. A slow ocean of liquid metal, 3,000 kilometers below your bed, is what makes life on Earth possible. And at the very center, the inner core. The inner core is a ball of solid iron and nickel, about 1,220 kilometers in radius, so roughly the size of the Moon. The temperature at the center of the Earth is estimated to be around 5,000 to 6,000 degrees Celsius, which is, and this is one of those facts that does not fully land the first time you hear it, roughly the same temperature as the surface of the Sun. Not the core of the Sun, which is unimaginably hotter, just the surface. The photosphere, the part that you see glowing in the sky. The center of the Earth is as hot as the surface of the Sun. And yet it is solid, because the pressure at that depth, the pressure from the weight of everything above it, is so extreme, around 360 gigapascals, that even at those temperatures the iron cannot become liquid. It is squeezed into solidity by the sheer mass of the planet sitting on top of it. This is the fire that never stopped. This is what has been burning since the Earth formed, 4.5 billion years ago. Where did it all come from? The heat, the original heat, the heat that has been slowly leaking outward for 4.5 billion years and has still not fully escaped. It came from the formation of the planet itself. In the very early solar system, a vast cloud of gas and dust was slowly collapsing under its own gravity, spinning faster as it contracted, most of the mass falling into the center to form the Sun, the rest flattening into a disk around it. In this disk, dust and ice and rock began to clump together, tiny grains sticking to each other, then small rocks, then boulders, then objects the size of mountains. Then, in a process called accretion that took tens of millions of years, the early Earth began to come together from billions of collisions, each collision releasing heat. Every rock that fell into the growing planet brought kinetic energy that became thermal energy, heat that built up faster than it could escape. And then, in the middle of this formation, something happened that we call the moon-forming impact. A body roughly the size of Mars, which astronomers have named Theia, struck the early Earth in a collision so catastrophic that the outer layers of both bodies were vaporized and thrown into orbit around what remained. This debris eventually coalesced into the Moon, and the energy released by that impact, there is no way to make that number feel real. The outer Earth was entirely molten. Not hot, entirely molten. A global magma ocean, kilometers deep, covering the whole planet. A magma ocean from which the first rocks slowly solidified as the surface cooled, which is why the earliest crustal rocks we have found date to roughly 4.4 billion years ago. The surface cooling slowly after that catastrophic beginning. The heat from that impact, the heat from accretion, the heat from the gravitational differentiation as heavy iron and nickel sank to the core through the molten early Earth. All of that heat is still there, still slowly conducting outward, still warming the mantle, still driving the convection cells that move the plates, still feeding, at certain points of weakness in the crust, the fires that we call volcanoes. 4.5 billion years, and it has not run out. It will not run out for a very long time. Billions more years, most likely. The Earth is a slow-burning thing, patient beyond any scale of patience that means anything to us. There is also a second source of heat that is less intuitive. The decay of radioactive elements inside the Earth. Isotopes of uranium, thorium, and potassium are naturally present in the rock of the mantle and crust, and as they decay, they release heat. Slow, constant nuclear heat from within the rock itself. This is not a small contribution. Estimates suggest that somewhere between a third and a half of the heat currently leaving the Earth's interior comes from radioactive decay rather than primordial heat. The planet is, in a very quiet sense, slightly radioactive, and the heat from that decay has been warming it from the inside for its entire history. So when you press your hand against a stone wall, the faint warmth you feel on a summer day is not just sunlight. Some small, almost undetectable fraction of that warmth has been on its way up from deep inside the Earth for longer than your mind can actually hold. Now, tectonic plates. There are 7 major plates and several smaller ones. The Pacific Plate is the largest, covering most of the Pacific Ocean floor. The North American Plate, the Eurasian Plate, the African Plate, the Antarctic Plate, the Indo-Australian Plate, the South American Plate. Then a collection of smaller plates, the Arabian Plate, the Caribbean Plate, the Juan de Fuca Plate, the Cocos Plate, the Nazca Plate, the Philippine Plate, and others. Each one a rigid slab of lithosphere riding on the softer asthenosphere below, being pushed from behind where new material rises from the mantle at mid-ocean ridges, and pulled from in front where old, heavy oceanic crust sinks back down into the mantle at subduction zones. The plates interact at their boundaries, and those boundaries are where most of the geological activity of the Earth is concentrated. Earthquakes, volcanoes, mountain ranges, they all cluster at plate boundaries, because those boundaries are where the forces are greatest, where the rock is being bent and broken and melted and remade. There are 3 kinds of plate boundaries. Divergent boundaries, where plates move apart from each other. The best example is the Mid-Atlantic Ridge, a chain of underwater mountains running almost the entire length of the Atlantic Ocean from Iceland down toward Antarctica. At the ridge, the North American and Eurasian plates are slowly pulling apart, and hot mantle material rises to fill the gap, creating new oceanic crust as it cools. Iceland sits directly on this ridge, which is why Iceland has so many volcanoes, and why it is one of the few places in the world where the Mid-Atlantic Ridge rises above sea level. You can stand in Iceland and put 1 foot on the North American plate and 1 foot on the Eurasian plate. Convergent boundaries, where plates collide. What happens depends on what the plates are made of. If 2 continental plates collide, neither one easily sinks because continental crust is too light and buoyant. So they crumple upward instead, forming mountain ranges. The Himalayas were made this way, the Indian subcontinent crashing slowly into Asia over tens of millions of years, pushing rock upward, still pushing, the Himalayas still growing, Mount Everest a millimeter or 2 taller every year. But if an oceanic plate collides with a continental plate, the oceanic crust, which is denser and heavier, sinks beneath the continental crust in a process called subduction. And as it sinks, as it descends into the hotter, higher pressure mantle, several things happen. The rock heats up. Water and other volatiles trapped in the oceanic crust are released as the rock is compressed and heated, and those volatiles rise up into the mantle above the subducting slab. And water, even a tiny amount, lowers the melting point of rock significantly. So the mantle above the subduction zone begins to melt, partially, in pockets, and that melt, now less dense than the surrounding rock, begins to rise, collecting in magma chambers, and eventually, in some cases, finding a path to the surface. A volcano. This is where the volcanoes of the Pacific Ring of Fire come from. The Ring of Fire, that horseshoe of volcanic and seismic activity that runs around the edges of the Pacific Ocean, from New Zealand up through the Philippines and Japan, across the Aleutian Islands to Alaska, and down through the American West Coast to Chile and back around. Every one of those volcanoes is sitting above a subduction zone. Every one of them is fed by magma generated by the melting of descending oceanic crust and the mantle above it, triggered by the introduction of water-bearing minerals being dragged down into the deep earth. This is, when you consider it quietly for a moment, an extraordinary recycling system. Old oceanic crust, made at a mid-ocean ridge, travels across the ocean floor for tens of millions of years, carrying whatever sediments settle on it, until it reaches a subduction zone and begins to descend back into the mantle. The mantle partially melts. The melt rises. It reaches the surface as lava and builds new rock. That rock eventually gets carried to another subduction zone, and the cycle continues. The same atoms have done this cycle multiple times over the history of the Earth. The rock in a volcano may have already been through the process before, several times before. Deep time makes that not just possible, but likely. And then there is the third type of boundary, transform boundaries, where plates slide past each other horizontally. The San Andreas Fault in California is the famous example. Here, the Pacific Plate and the North American Plate are moving past each other, the Pacific Plate moving northwest relative to North America. No crust is being created or destroyed, just two massive slabs of rock grinding slowly against each other, building up stress over decades and then releasing it suddenly in earthquakes. Transform boundaries do produce some volcanism, but it is less common than at divergent or convergent boundaries. But not all volcanoes are at plate boundaries. Some of the most famous, most active volcanoes in the world are sitting in the middle of a plate, far from any boundary. And the explanation for this is what geologists call a hot spot. Imagine a plume of heat rising from the deep mantle, maybe even from the boundary between the mantle and the outer core. A narrow column of hotter-than-usual mantle material, rising because it is slightly less dense than what surrounds it, rising slowly over millions of years, rising until it reaches the base of the lithosphere, where it spreads out and partially melts the overlying rock. The melt rises through the crust, and a volcano forms on the surface directly above the plume. The thing is, the plume does not move, or it moves very little. It is rooted deep in the mantle, perhaps all the way at the core mantle boundary. But the plate above it is moving, slowly, at the rate of fingernail growth. So the volcano that forms above the plume gradually moves away from it as the plate carries it along. The volcano over the hotspot goes dormant as it drifts away from the heat source. And then a new volcano forms behind it, where the plate is now directly above the plume. And that one gradually moves away too, and so on. What this produces over millions of years is a chain of extinct volcanoes stretching across the ocean floor, each one older the further it is from the current hotspot. A geological record of where the plate has been, written in mountains of basalt. And the most perfect example of this in the world is Hawaii. The Hawaiian Islands are the most recent expression of the Hawaii hotspot, a plume that has been burning through the Pacific Plate for at least 70 million years, possibly longer. The Big Island of Hawaii, which geologists sometimes call just the Big Island, to distinguish it from the state, is currently sitting directly over the hotspot, which is why it has active volcanoes. Kilauea, on the Big Island's southeastern flank, is one of the most continuously active volcanoes on Earth. Mauna Loa, also on the Big Island, is the largest volcano on Earth by volume, an enormous shield volcano that has built itself up from the ocean floor over hundreds of thousands of years. As you travel northwest along the Hawaiian chain, the islands get older. Maui is slightly older than the Big Island, having drifted off the hotspot. Oahu, where Honolulu is is older still, its volcanoes long extinct, eroded by wind and rain into the gentle green shapes of the Kewalow and Waianae ranges. Kauai, the oldest of the main Hawaiian islands, is so old and so eroded that it barely resembles a volcanic island anymore, just a green, wrinkled jewel in the ocean. And if you continue northwest of Kauai, the chain continues. Not as islands above the sea, because the volcanoes have been eroding for so long and the ocean floor beneath them has been slowly sinking as it cools, but as seamounts just below the surface. The Midway Atoll. And beyond that, further northwest, the chain bends. Because about 47 million years ago, the Pacific plate changed direction slightly. You can see the bend in the chain, a geological record of a plate changing course, preserved in the positions of seamounts across the ocean floor. 70 million years of movement, recorded in stone, stretching across the Pacific. The Big Island is the youngest, still being built, still being fed by the hotspot below. There is already a new volcano forming on the ocean floor southeast of the Big Island, a seamount called Loihi, still about a kilometer below the surface, being built up slowly by lava from the same hotspot. In maybe 10,000 to 100,000 years, Loihi will break the surface. A new island, already being born. The hotspot does not care that we will not be here to see it. The hotspot does not care about any timescale we find relevant. It has been doing this for 70 million years and will continue doing it long after every trace of us has been absorbed back into the rock. The magma that feeds Kilauea right now is rising from the mantle, from somewhere around 60 to 80 kilometers below the surface, ascending through the lithosphere in a column of heat, pooling in shallow magma chambers beneath the volcano, finding pathways through the rock, filling old passages and forcing new ones, and eventually reaching the surface where it pours out as lava, red-orange at the vent, darkening as it cools, building new land at the edge of the ocean. Land that is being walked on by birds and insects within years, colonized by plants within decades, covered in forest within centuries. The newest land on Earth, still warm from the inside. Right now, as you lie there, somewhere on the southeastern slope of Kilauea, lava is probably moving. Not dramatically, not necessarily fountaining, maybe just slowly oozing from a crack in the ground. Pahoi lava, the smooth, ropey kind that moves almost lazily, curling over itself as it goes. The outer crust hardening in the air, while the molten interior continues forward underneath. It is not a disaster. It is not a spectacle. It is just the Earth doing what it has always done, building new ground from the inside, extending the edge of the island a few centimeters into the sea. And beneath all of that, beneath the lava flows and the magma chambers and the lithosphere and the convecting mantle and the liquid iron outer core, at the very center of everything, that ball of solid iron as hot as the surface of the sun is sitting there in total silence, squeezing the heat outward in every direction, as it has done for 4.5 billion years. It has never stopped, not once, not for a single moment in all of that time. And the surface of this planet, this thin, cool, habitable shell of rock, has ridden on top of it all, slowly rearranging itself, building continents and dismantling them, opening oceans and closing them, burying mountain ranges under new seas and lifting the sediments of ancient seas into new mountain ranges, never stopping, never settling, never being finished. 250 million years ago, all the continents were joined together in one supercontinent that geologists call Pangaea. Before that, other configurations, Other supercontinents. Rodinia, a billion years ago, now entirely dispersed. Gondwana, Colombia. Each one assembled over hundreds of millions of years, then slowly torn apart, then reassembled differently. 200 million years from now, the continents will be in entirely different positions again. The Atlantic Ocean will be closing as the Americas drift back toward Europe and Africa. The Mediterranean will have closed entirely. A new supercontinent, sometimes called Amasia or Pangaea Proxima by scientists who like to think that far ahead, will be assembling in the northern hemisphere. None of this is guesswork. It follows from the physics of plate tectonics, from the convection patterns in the mantle, from the measured velocities of the current plates. You can model it forward the same way you can model it backward. And driving all of it, the same heat, the same slow fire inside. The floor beneath you right now has been, at various points in the deep past, near the equator, beneath a tropical sea, buried under kilometers of ice, volcanic landscape, shallow lagoon, desert, deep ocean floor. And now here, wherever you are, under a house or apartment, under carpet or wood or concrete, solid and still and familiar. All of that history in the rock beneath you, and not a trace of it visible in the dark of your room tonight. The Earth moves slowly enough that it looks still to us, which is a remarkable coincidence, really. If the plates moved 10 times faster, we would all be very aware of them. There would be constant visible ground movement, constant reshaping of coastlines within a lifetime. But at 1 to 2 centimeters per year, it is invisible to us. We live entire lives without once feeling the continent drift. What we do feel, sometimes, is when the plates catch and jolt at their boundaries. Earthquakes. A sudden release of stress built up over decades. But even those are just a symptom, a momentary noise in a much slower, quieter process. Volcanoes are the other symptom. But more than symptoms, they are valves. The Earth's interior needs to release heat, and volcanoes are some of the pathways through which it does that. They are also, and this is something that tends to get lost in disaster narratives, some of the most important things that have ever happened to this planet. Without volcanoes, Earth might look very different. Might look like Mars. Bare, cold, thin atmosphered, silent. We will get to that. The Pacific Plate right now is moving northwest at about 7 centimeters per year. Faster than fingernail growth, faster than most plates. It has been carrying the Hawaiian chain northwest for millions of years. The Pacific Plate is also subducting beneath Japan, beneath the Philippines, beneath the west coast of South America. At all those places where it disappears back into the mantle, it generates the magma that feeds the volcanoes of the Ring of Fire. Japan sits on the boundary where the Pacific Plate and the Philippine Sea Plate are both subducting beneath the Eurasian Plate, which is part of why Japan has over 100 active volcanoes and some of the highest earthquake frequency of any country on Earth. The country is being built and shaken simultaneously by the same forces. Mount Fuji, which is Japan's most famous volcano, last erupted in 1707. It is considered dormant, not extinct. The distinction matters. Extinct volcanoes are ones where the magma supply has been cut off permanently, usually because the plate has moved far enough from the hotspot or the subduction zone to no longer be generating melt. Dormant volcanoes still have a connection to magma below, but have not erupted in historical time, or have erupted infrequently enough that their eruptive potential sometimes gets underestimated. Fuji is dormant. The magma is still there below it. The geological conditions that made it erupt in 1707 have not fundamentally changed. There is a monitoring network watching it constantly, and Fuji is just one of the examples where what looks like permanent stillness is actually something more like patience. The fire beneath is still there, still being fed, still waiting for conditions to change in ways that would let it move. Volcanoes wait. That is the other thing about them that does not fit the disaster documentary version of events. They are patient. Some erupt frequently, some go centuries between eruptions, some go millennia. But the connection to the interior is rarely fully severed. The rock remembers. The heat is still there. The Cascade Range in the American Pacific Northwest, Mount Rainier, Mount Hood, Mount St. Helens, Mount Shasta, each one a stratovolcano sitting above the subduction of the Juan de Fuca Plate beneath the North American Plate. Mount St. Helens erupted dramatically in 1980, in an eruption that remains one of the most studied in history, an eruption that began with a massive landslide of the north face of the mountain and released energy equivalent to thousands of nuclear bombs. Before that eruption, St. Helens had been dormant since 1857. 123 years of apparent sleep, and then it woke up. The others in the Cascades are watching. Rainier especially. Rainier is considered by many geologists to be one of the most dangerous volcanoes in the United States, not necessarily because of its likelihood of erupting soon, but because of what would happen if it did. The mountain holds more glacial ice than any other peak in the continental US, and an eruption could generate massive lahars, volcanic mudflows, that would travel rapidly down the river valleys toward populated areas. Tacoma and parts of Seattle are built on lahar deposits from previous Rainier eruptions. The ground those cities are built on was put there by the mountain, which is, when you think about it in a particular way, the mountain providing for the valley. The rich, mineral-laden volcanic deposits making some of the most fertile soil in the region. The volcano that threatens is also the volcano that gave. That tension, threat and gift, destruction and creation, runs through everything in the story of volcanoes. It is not one or the other. It has never been one or the other. And you, lying there in the dark, on the thin shell of rock above the fire, are here in part because of what that fire gave the earth. The air you are breathing right now, the slow in and out of it as you relax, has a history that starts in eruptions older than anything we have a name for. The water in your body, the minerals in the ground that grew the food that made you. All of it, in the very longest view, coming from the heat below. The crust is about, on average, 30 kilometers thick under the continents. 30 kilometers between you and rock that is soft enough to flow, given time. 30 kilometers of solid, familiar stone, that thinnest imaginable shell, and then below it, the slow, impossible engine that has been running since before the sun had planets. Right now, somewhere beneath the Pacific Ocean, at a mid-ocean ridge, new crust is being born. Hot mantle rock is upwelling, cooling as it rises, crystallizing into basalt, being pushed away from the ridge on both sides as more rises behind it. New seafloor. New rock that did not exist before today. Being created at this moment, in total darkness, under kilometers of water, with no witness except the instruments we have left there to listen. And somewhere else in the Pacific, that same type of rock, millions of years older, is descending into a subduction zone, being pushed back into the mantle, melting, becoming the source for a volcano somewhere on the surface above. Maybe one that has not yet erupted in human memory, maybe one that erupted last week. It is a cycle so slow that from inside a human life it looks like geology, looks like history, looks like something that happened and is now fixed and finished. But it is not finished. It is ongoing. It is happening at this moment, at every moment, in the dark and the pressure and the heat, far below the surface of everything. And somehow, the floor beneath you feels more solid for knowing that. Not less, more. Because the fire that is down there, that restless, ancient heat, is also the reason the floor is there at all. The reason there is any crust to live on. The reason there is any air to breathe. The reason there is a planet rather than just a cold, dark, airless rock drifting around a star. The heat made all of this. 4.5 billion years ago, the Earth was just beginning to sort itself out, layers forming as heavy material sank and lighter material rose, the surface still half molten, no land visible anywhere, no ocean yet formed, the sky a thick, choking mass of volcanic gases and steam. And from that chaos, slowly, over millions of years, something like a planet began to emerge. The steam condensed, the oceans filled, and the fire settled into its long, patient burning. The burning that has never stopped. The burning that is still happening right now. Below everything. Below you. Below the floor. Below the rock. Below the slow rivers of the mantle, down to that iron heart spinning quietly at the center of the world. But let's stay closer to the surface for a while. Let's talk about what happens when the heat actually breaks through. Magma. That is the word for it, when it is underground. Still inside the earth. Still rising. Still working its way through cracks and chambers in the rock. Magma. And the moment it reaches the surface, the moment it crosses that threshold into open air or open water, it becomes lava. The same material, same temperature roughly, same composition mostly, just a different word for where it is. Which is one of those distinctions that seems overly technical until you realize it actually matters. Because magma and lava behave differently in their environments, in ways that change everything about how a volcano acts. Magma underground is under pressure. It contains dissolved gases, mostly water vapor, carbon dioxide, sulfur dioxide, some hydrogen sulfide. Dissolved in the melt, the way carbon dioxide is dissolved in a sealed bottle of sparkling water. And as magma rises toward the surface, the pressure decreases. And as the pressure decreases, the gases start to come out of solution, the way a bottle of sparkling water fizzes when you open it. This exsolution of gases is one of the key factors in determining how violent an eruption will be. The other key factor is viscosity. How thick the magma is, how easily it flows. And viscosity depends largely on composition. Specifically on silica content. Magma with low silica content, called basaltic magma, is thin and runny. It flows easily. The gases dissolved in it can escape gradually as the magma rises, venting quietly rather than building up pressure. Low viscosity magma tends to produce gentle, effusive eruptions. Rivers of lava flowing down the mountain's slopes rather than explosions. The Hawaiian volcanoes produce basaltic magma. Kilauea's eruptions are generally non-explosive, lava flows rather than blasts, spectacular and dangerous in their own way, but not the ash column into the stratosphere kind of event. Magma with high silica content, called rhyolitic magma, is thick and sticky. Viscous enough that the dissolved gases cannot escape easily. They build up inside as the magma rises, pressure accumulating, unable to vent, until finally the pressure overwhelms the rock above, and the whole thing releases at once, in an explosion that can be orders of magnitude more violent than anything the Hawaiian volcanoes do. Yellowstone produces rhyolitic magma. The volcanoes of the Andes, sitting above the subducting Nazca Plate, tend toward the viscous end of the spectrum. And then there is the intermediate category, andesitic magma, named for the Andes, which sits between basaltic and rhyolitic in terms of both silica content and viscosity. Most of the volcanoes of the Ring of Fire produce andesitic magma, which means their eruptions can range from relatively gentle lava flows to significant explosive events, depending on the exact composition and the amount of dissolved gas and the conditions in the magma chamber. Stratovolcanoes, the classic cone-shaped peaks like Fuji and Rainier and Etna and St. Helens, are typically built from andesitic or dacitic magma, alternating layers of lava and pyroclastic material, ash and rock fragments blasted out during more explosive phases. What does magma actually look like? Not the way movies show it. It is rarely the thin, cherry-red liquid glowing uniformly orange that gets used in special effects. Real magma, especially the more viscous types, is thicker than you expect. Heavy. It moves with a kind of reluctance, dragging itself forward. At the vent of a lava flow, the surface crusts almost immediately in contact with the air, forming a dark, rough skin that cracks and breaks as the still molten interior pushes forward underneath. The glow is visible through those cracks, orange and yellow, and at night it is genuinely extraordinary to see. These dark plates of cooling rock floating on a river of orange light. The temperature of lava at the vent is typically between 700 and 1,200 degrees Celsius, depending on composition. The saltic lava is hotter, around 1,100 to 1,200 degrees. Rhyolitic lava is cooler, relatively speaking, around 700 to 900 degrees. Hot enough that the air above a lava flow shimmers so intensely it distorts everything behind it. Hot enough that you can feel the radiant heat from tens of meters away, a wall of warmth pushing outward in every direction. And yet, there is a quality to watching lava flow that people who have seen it describe not as terrifying, but as hypnotic, patient, almost slow. It does not rush. It goes where gravity takes it, filling depressions, following the lowest path, occasionally pooling, and then finding a new way forward. It is not trying to do anything. It is just heat and weight, and the slow patience of melted rock doing what melted rock does. Kilauea. Kilauea, on the southeastern flank of the Big Island of Hawaii, is one of the most visited and most studied active volcanoes on Earth. It has been erupting, with some brief pauses, since 1983, continuously. That is over 40 years of essentially unbroken volcanic activity from a single volcano. Think about what that means in human terms. People were born and grew up and graduated and had children of their own in the time that Kilauea has been erupting. Entire careers at the Hawaiian Volcano Observatory have been built on watching this one volcano. It has become something like a neighbor, familiar, known. Scientists there can read its behavior almost the way you learn to read a person's mood over years of proximity. The 1983 eruption began at the Pu'u'o'o vent on Kilauea's East Rift Zone. Rift zones are regions of weakness in the flank of a volcano where the rock is fractured and magma finds it easier to intrude. The East Rift Zone of Kilauea runs for about 125 kilometers, and along this zone, eruptions have occurred repeatedly throughout the volcano's history. The Pu'u'o'o eruption built a cone over the years, changed character dozens of times, produced lava flows that covered over 100 square kilometers of the Big Island's surface, added new land to the coast where flows entered the sea. When lava enters the ocean, it does something that is, in a small way, extraordinary every single time. The seawater flash boils on contact with the 1,100-degree lava, creating billowing white plumes of steam and hydrochloric acid gases. The lava itself, cooling so rapidly, shatters into glassy fragments, a kind of natural obsidian. But underneath the surface, in deeper water, the cooling is slower, and the lava forms what are called pillow lavas, bulbous, rounded masses of basalt that pile up on each other like stacked pillows. Pillow lavas are found all over the world on ancient ocean floors. They are, in fact, one of the ways geologists identify old seafloor that has been thrust up onto land by tectonic activity. A field of pillow basalts in a mountain range is a record of an ancient ocean floor. New land being made, at this exact moment probably. In the dark, in the warm Pacific water, in May 2018, Kilauea entered a new and more dramatic eruptive phase. Dozens of fissures opened in the lower East Rift Zone, in a residential area called Leilani Estates. Lava fountained from cracks in roads and backyards. Entire streets were buried. Homes were consumed. And at the summit, the lava lake that had been sitting in the Halema'uma'u crater, a lake of molten rock that had been there for years, drained rapidly as the magma migrated down the rift zone, and the crater collapsed in a series of explosive, steam-driven eruptions as groundwater came into contact with the hot rock exposed by the collapse. The eruption lasted months. When it was over, Kilauea had changed shape. The summit crater had grown dramatically. New lava fields covered a swath of the lower East Rift Zone. And when the eruption ended and scientists returned to assess what had happened, a new lava lake had already begun to form in the enlarged summit crater. The volcano continued. Then there is Stromboli. Stromboli is a small island off the coast of Sicily in the southern Tyrrhenian Sea, one of the Aeolian Islands, a volcanic archipelago that includes several other active volcanic features. The island is essentially entirely made up of the volcano, a steep-sided cone rising about 924 meters above sea level, and a great deal more below the sea surface. Stromboli has been erupting, persistently and regularly, for at least 2,000 years. Possibly much longer, but the written record gets thinner the further back you go. The eruptions are not large, not dramatic in the sense that they threaten widespread destruction. Every 20 minutes or so, roughly, give or take because it is a volcano and not a clock, Stromboli erupts. A burst of gas and fragmented lava, incandescent clots of magma thrown into the air above the summit craters, sometimes climbing 100 to 200 meters above the vent. A flash of light, a deep rumbling, a shower of glowing ejecta, some of which falls back into the craters, some of which rolls down the Schiara del Fuoco, the trail of fire, a steep slope on the northwest flank of the volcano that leads directly into the sea. Then silence for a while, then another burst. For 2,000 years. Ancient sailors used Stromboli as a lighthouse. The flashes from the summit, visible at sea at night, guided ships in the Tyrrhenian Sea long before anyone had built a lighthouse on the island. The lighthouse of the Mediterranean, they called it. A natural feature so regular, so reliable, so persistent that it became useful navigation. 2,000 years of eruptions. The sailors who used it as a lighthouse are dust. The civilizations they sailed for are long gone. The ships they sailed on have dissolved back into the sea. And Stromboli is still erupting every 20 minutes, more or less. Still flashing in the dark. Still patient. Still doing exactly what it has always done. Etna. Mount Etna, on the island of Sicily, is the largest active volcano in Europe by volume, and one of the most active in the world. It rises to about 3,357 meters above sea level, though that number changes after significant eruptions because Etna adds to its own summit with each eruptive episode. The volcano is visible from much of Sicily and from the Strait of Messina on a clear day, and on nights when it is erupting actively, the glow from its summit craters can be seen from ships far out at sea. Etna has been erupting for at least 500,000 years. The civilizations that grew up around it, Greek colonies, Roman settlements, medieval towns, modern Sicilian cities, all of them knew they were living in the shadow of an active volcano. The ancient Greeks believed Etna was the forge of Hephaestus, the smith god, where his cyclops worked to make the lightning bolts of Zeus. There is a version of the Typhon myth that places the defeated monster Typhon beneath Etna, his struggles causing the eruptions. The Romans thought similarly. Etna was above something restless. They were not wrong. Etna sits at a complex tectonic junction. Sicily is part of the African plate's leading edge as it slowly converges with the Eurasian plate. The volcanism of southern Italy, of Etna and Stromboli and Vesuvius, is partly related to this convergence and partly related to more complex local subduction dynamics in the southern Tyrrhenian Sea. The exact plumbing of Etna is still actively debated by volcanologists. It has deep roots, maybe deeper than standard subduction-related volcanism would suggest. There may be a component of mantle plume activity involved. The Earth does not always sort its own geology neatly into categories. Etna erupts frequently, multiple times per year in recent decades. Lava flows, lava fountains, ash columns, sometimes all three in the same eruptive episode. The flanks of the mountain are covered with the traces of centuries of lava flows, dark ribbons of old basalt winding down through vineyards and forests and the outskirts of towns. The towns themselves are sometimes built partly on old lava flows. The fertile soil of the Etna region, some of the best agricultural land in Sicily, comes from the gradual weathering of volcanic rock. The same volcanic rock that threatens the towns also feeds the vines. Etna is not threatening right now in any unusual sense. It is just doing what it does. Erupting, moving magma, building itself up slowly, being Etna. Pompeii. The eruption of Vesuvius in 79 AD is probably the most famous volcanic event in recorded history. Everyone knows the basic outline. The mountain erupted, the city was buried. That much is in the popular consciousness. But the details, and what happened to what was buried, are worth dwelling on slowly. Pompeii was a prosperous Roman city of somewhere between 11,000 and 20,000 people, situated about 9 kilometers from Vesuvius on the Bay of Naples. It was a port city, a commercial city, a city with baths and amphitheaters and brothels and bakeries and temples. A city that felt, to the people living in it, like it had been there forever and would be there forever. In the late summer of 79 AD, Vesuvius had been rumbling for days, maybe weeks. There had been earthquakes. They were accustomed to earthquakes in that region, part of the same volcanic geology that produced Vesuvius. The people of Pompeii did not have the concept of a volcanic eruption as we understand it. Vesuvius had not erupted in historical memory, certainly not within anyone alive in 79 AD's memory. There were no volcanologists. There was no monitoring network. There were just people living their lives in a city under a mountain. On the 24th of August, or possibly late October, scholars have debated the date based on Pliny the Younger's account and on the discovery of seasonal foods and clothing in the ruins. Vesuvius erupted with enormous violence. A column of ash and gas and fragmented rock, a Plinian column named for Pliny the Elder who died observing the eruption, rose 30 kilometers into the sky. For hours, ash and pumice rained down on Pompeii. Buildings began to collapse under the weight. Then came the pyroclastic surges. A pyroclastic surge is a fast-moving current of hot gas and volcanic material, denser than air, flowing down the slopes of a volcano at speeds that can exceed 700 kilometers per hour. The temperatures inside a pyroclastic surge can reach several hundred degrees Celsius. Nothing in its path survives. The people of Pompeii who had not already fled were killed almost instantaneously by the heat of the surge, their bodies preserved in the positions they were in at the moment of death by the rapidly accumulating volcanic ash that hardened around them. Not slow suffocation. The heat killed them first, and then 4 meters of ash. And then, in a way that no one planned and no one intended, that ash preserved Pompeii almost perfectly for nearly 1,700 years. When archaeologists began serious excavation of the site in the 18th century, they found a city frozen in mid-afternoon on a day in 79 AD. Bread still in the ovens, food on the tables in Thermopolia, the Roman fast food establishments where hot food was kept in terracotta containers set into stone counters. Political graffiti on the walls, campaign slogans for local elections, love poetry, insults, bawdy jokes. The full, ordinary, messy texture of daily life in a Roman city, preserved because of a catastrophe, because of a volcano that did the one thing that nothing else could have done, which was seal it all away from time. We know more about daily life in a mid-sized Roman city in the 1st century AD than we know about almost any other ancient urban culture because of Vesuvius. The volcano that killed Pompeii also saved it. The hollow spaces left where organic material decomposed inside the hardened ash, the people, the wooden furniture, the cloth, the food, could be filled with plaster to create exact casts. The famous plaster casts of the Pompeii victims. People in the last moments of their lives, curled up, covering their faces, lying next to each other. One is a dog, still chained to a post, the chain still visible in the cast. They are extraordinarily moving objects, because they are not artistic representations of death. They are death's exact shape, preserved in the negative space of a volcano's aftermath. Vesuvius is still there, of course, 9 kilometers from Naples, ringed by one of the most densely populated areas in Italy, considered a dormant, not extinct volcano. Its last eruption was in 1944. Volcanologists watch it continuously. There are evacuation plans, but the city of Naples and its surroundings are enormous, and the logistics of evacuating millions of people quickly enough in the event of a major eruption are, frankly, something that authorities do not discuss with full optimism. It has not erupted since 1944, but it last had a major Plinian eruption in 79 AD. The interval between major Plinian eruptions at Vesuvius, when you look at the geological record, varies. But the intervals have historically been measured in centuries to millennia, which means the next major eruption at Vesuvius, statistically speaking, at the broad scale of geological time, is not necessarily imminent, but it is also not impossible. It is, in the language volcanologists use carefully, a matter of when, not if. But that is a thought for daylight. For right now, for this moment, Vesuvius is quiet. The monitoring instruments are showing nothing alarming. The magma beneath it is not rising significantly. The ground is not inflating. The mountain is doing what it does between eruptions, which is sit there, dark and large and quiet, the lights of Naples glowing beneath it in the night. Krakatoa, or Krakatau, which is the more accurate Indonesian pronunciation, though both names appear in the historical literature and both refer to the same place, more or less. In August of 1883, the Krakatoa volcanic island, sitting in the Sunda Strait between Java and Sumatra in what is now Indonesia, underwent one of the largest and most consequential volcanic eruptions in recorded history. The eruption had been building for months. There had been increasing seismic activity, steam and ash emissions, smaller explosive events throughout the summer of 1883. But on the 26th and 27th of August, the eruptions became catastrophic. A series of massive explosive events culminated in a cataclysmic caldera collapse on the morning of August 27th. The explosion was heard over 4,800 kilometers away, on the island of Rodriguez near Mauritius, where observers reported hearing what they thought were ship cannons in the distance. It was later established to be the loudest sound ever documented in recorded history, a sound wave that traveled around the Earth multiple times and was still detectable by barographs over a day later. The eruption generated a tsunami, or more accurately, a series of tsunamis, as the sudden collapse of the volcanic edifice into the ocean displaced enormous volumes of water. The tsunamis struck the coasts of Java and Sumatra, with waves reaching up to 30 meters in height in some places, killing an estimated 36,000 people. The ash and sulfur dioxide gases injected into the upper atmosphere circulated globally. The following 18 months saw global average temperatures drop by about 1.2 degrees Celsius. Sunsets all over the world turned vivid, unusual colors, reds and oranges more intense than normal, caused by the scattering of sunlight by the fine particles suspended in the upper atmosphere. The Norwegian painter Edvard Munch would later say that the intense red sky in his famous painting, The Scream, was inspired by the skies he saw after the Krakatoa eruption. That painting, that screaming anxiety of red sky over blue fjord, may be partly a record of volcanic aerosols in the stratosphere. The original Krakatoa island mostly collapsed into the caldera in 1883, but the volcanic system underneath was not finished. In 1927, a new island began to emerge from the sea in the middle of what had been the old Krakatoa caldera. Anak Krakatau, Child of Krakatoa in Indonesian. It has been growing ever since, intermittently erupting, building itself up from the sea floor, a new volcanic island being assembled from the same geological system that produced the 1883 catastrophe. In 2018, Anak Krakatau underwent a significant flank collapse during an eruption, triggering another tsunami that struck the coasts of Sumatra and Java with little warning, killing hundreds of people. The collapse reduced the island's height dramatically, but it has already started rebuilding. The volcanic system does not stop. It does not exhaust itself. It just changes shape. And then Tambora. The 1815 eruption of Mount Tambora on the island of Sumbawa in Indonesia is the largest volcanic eruption in recorded history in terms of the volume of material ejected. The volcanic explosivity index, the scale used to measure the size of eruptions, goes from 0 to 8, with each step representing a roughly tenfold increase in the volume of ejected material. Tambora was a 7. For comparison, the 1980 St. Helens eruption was a 5. Krakatoa in 1883 was a 6. Tambora ejected an estimated 160 cubic kilometers of material. The eruption killed approximately 71,000 people directly, making it the deadliest volcanic eruption in recorded history in terms of immediate casualties. But the after-effects spread much further. The enormous volume of sulfur dioxide injected into the stratosphere by the Tambora eruption created a stratospheric aerosol layer that reflected solar radiation back into space, cooling the Earth's surface. 1816 became known in the Northern Hemisphere as the year without a summer. In Europe and North America, temperatures in the spring and summer of 1816 were anomalously cold. Snow fell in June in New England. Frosts occurred in July and August across much of Europe. Crops failed. Widespread food shortages and famine followed. In parts of Europe, the famine was severe enough to trigger social unrest and mass migration. In China and India also, affected by the cooling, monsoon patterns were disrupted and food production fell. The poet Byron was in Switzerland in the summer of 1816 at the Villa Diodati near Lake Geneva with Mary Godwin and Percy Shelley and John Polidori. The summer was so cold and stormy that they were largely confined indoors. Byron proposed that each member of the group write a ghost story. Mary Godwin, who would soon become Mary Shelley, wrote the story that became Frankenstein. Polidori wrote The Vampire, which was the first modern vampire story in the English tradition. Both of those books, and all the cultural work that has descended from them, the entire vampire genre in literature and film, and the entire Frankenstein tradition in fiction, and the philosophical questions it raises about creation and responsibility, can in some sense trace their existence to the eruption of a volcano in Indonesia in 1815. A volcano in Indonesia changed the weather in Switzerland in 1816 and led directly to the creation of the modern horror genre. That is not poetry. That is meteorology and literary history coinciding. The 1815 eruption also decimated the population of Sumbawa and neighboring islands. The Tambora people, who had lived on the mountain slopes, had their own language, culture, material traditions, none of which survived. The entire society was essentially destroyed in a single night. The Tambora language went extinct in the eruption of the volcano that shared its name, spoken by people who lived on a mountain that destroyed them, and now there is no one left who remembers what it sounded like. That is a loss of a kind that does not have a standard category in how we think about things being lost. The mountain itself was reduced from an estimated 4,300 meters in height to 2,851 meters. The caldera left behind is 6 kilometers across and 1 kilometer deep. You could fit a small city in it. Researchers who have descended into the caldera have found, beneath the layers of volcanic material, evidence of the civilization that was there before. Pottery, the foundations of buildings, objects of daily life, fused and warped by heat. A Pompeii, essentially, buried under its own mountain. Tambora is still active, classified as a potentially active volcano. It has had minor eruptive activity since 1815. The magma system that produced the 1815 eruption is still there below. Sleep Science has featured volcanic eruptions before, in other contexts, but the scale of Tambora is something that deserves to sit with you quietly for a moment. Not in fear, just in proportion. The sense of scale that comes from understanding how a single geological event can ripple through the climate, through the harvests, through the politics, through the literature, through the entire culture of a century, all from a single violent release of pressure from inside the Earth. The Earth makes its presence known occasionally. Not often, not on any timescale that feels threatening from inside a single human life, but occasionally. And when it does, the effects travel far. The thing about all of these eruptions, Vesuvius and Krakatoa and Tambora and St. Helens, and every eruption that came before them, and every eruption that will come after, is that they are not failures of the system. They are the system working. They are the inevitable expression of the physics of a planet that has never stopped generating heat and never found a way to release all of it gradually. Pressure builds. Something gives. Material moves. Heat escapes. The system adjusts. It is not malevolent. It is not indifferent in the way we sometimes mean indifferent, as a kind of cold hostility. It is just a physical process of enormous scale and enormous patience, operating on timescales so different from ours that our entire recorded history is not even a rounding error. And there is something that should probably feel frightening about that, but somehow does not. At least not at this hour, in the quiet of wherever you are. Because the very same process, the very same heat that occasionally produces a Krakatoa or a Tambora, is the process that made this planet alive. The process that gave the air its nitrogen and its oxygen, eventually. The process that gave the oceans their water. The process that is, even now, building new land at the edges of Hawaii and Iceland, and at the bottom of the sea, where no one will ever see it. You are breathing air that volcanoes made. The carbon in your body cycled through volcanic vents long before it cycled through anything alive. The minerals in the soil that grew the food that you ate today were put there, in the long geological chain of cause and effect, by eruptions older than any continent in its current form. The fire gave you everything, and it has never asked for anything in return, never made a bargain, never noticed you at all. It just burns, as it has always burned, as it will always burn, slowly and enormously and without pause, in the dark at the center of the world, while above it the thin shell of rock cools in the night air, and the oceans shift gently, and the plates move at the speed of growing fingernails, and every living thing on the surface of this planet goes about its brief, extraordinary, borrowed existence, built entirely on the heat below. Right now, somewhere in Iceland, where the mid-Atlantic ridge crosses above sea level, a fissure in the Reykjanes Peninsula may be venting steam. Iceland has been in a period of elevated volcanic activity in that region, multiple eruptions since late 2023, lava flows covering old lava flows, the landscape being actively remade. The people of Grindavik, a town that has had to be evacuated multiple times as eruptions approached, have had the strange experience of watching the earth build new ground around the edges of their town while they waited to return to it. New ground, being made. Not 70 million years ago over the Pacific, right now, this year, last month probably. The earth building itself in real time while people stood at barriers and watched. There are around 1,350 potentially active volcanoes on the land surface of the Earth. Of those, about 500 have erupted in recorded history. At any given moment, roughly 20 are erupting simultaneously. 20 volcanoes erupting right now, tonight, as you lie there. Most of them quietly, without anyone paying much attention. A fissure vent on the big island of Hawaii, a lava lake in a crater in the Democratic Republic of Congo, a persistent eruption column rising from a volcano in Papua New Guinea. Stromboli, as always, every 20 minutes, its summit flickering in the dark. 20 volcanoes, right now, all of them connected, in the end, to the same heat, the same deep fire, the same origin. And beneath all the others, the ones currently quiet, the ones that have not erupted in centuries or millennia, the magma is still there. Still being replenished from below, still being heated by the slow creep of the mantle, still waiting, with the patience of a geological system, for conditions to align, for the pressure to build far enough, for a pathway to open. The Earth is not done building itself, not by a very, very long way, which means the volcanoes are not done either. Not Etna, which will almost certainly erupt again in the coming months, because Etna is always erupting or about to erupt. Not Vesuvius, which is quiet now, but which sits above one of the most complex and active magmatic systems in Europe. Not the Cascade volcanoes, slowly building pressure as the Juan de Fuca plate continues its long descent. Not Yellowstone, which breathes through its geysers and hot springs the way a sleeping person breathes, steadily, in and out, giving no indication of what it might do if it ever chose to fully exhale. Not any of them. They wait, with more patience than anything we know how to name. And the ground above them, the ground you are lying on, the ground that holds your house and your street and your town, is just the most recent arrangement of material that the Earth's interior has pushed toward the surface, cooled, and declared, temporarily, solid ground. Temporary on geological timescales, permanent on human ones, which is the tension at the heart of living on this planet. The floor feels permanent because our lives are short, and in the context of a human life, it is permanent. It will hold you. It will be there tomorrow. The house will not slide into the mantle tonight. The road will be where you left it. The mountain on the horizon, whether it is a volcano or not, will be in the same place when the sun comes up. But the rock you are lying on has a history that goes back hundreds of millions of years, and a future that extends just as far. And in both directions, it is full of change, full of movement, full of the slow rearrangement of material by heat from below. The crust is not done moving. The mantle is not done convecting. The core is not done cooling. Or rather, it is cooling, but so slowly that the word cooling does not quite capture it. A degree or two over hundreds of millions of years. A process so gradual that the heat from the beginning of the solar system is still largely there, still doing its work, still driving the engine that moves the plates and feeds the volcanoes and keeps this planet geologically alive. Because that is the other thing. The Earth is geologically alive. Mars is not. Mars cooled too quickly, its interior solidifying, its magnetic field dying, its tectonic activity ceasing billions of years ago. The surface of Mars is essentially unchanged from what it was 2 or 3 billion years ago. Old craters, old volcanoes, long dead. Olympus Mons, the largest volcano in the solar system, is on Mars, a shield volcano so enormous it covers an area roughly the size of France and rises 22 kilometers above the surrounding plain. But it is extinct, has been extinct for perhaps 25 million years, possibly longer. The magma system that fed it ran out of heat. The interior cooled and stiffened. The engine stopped. And now Mars is silent, geologically silent. The craters stay where they were made. The dust moves, but the rock does not. Nothing is being built. Nothing is being recycled. The planet is, in the geological sense, finished. Earth is not finished. Earth is still in the middle of its story. And the reason, the deep reason, the physical reason underneath everything else, is that the Earth is bigger than Mars. Big enough that the heat from its formation and from the radioactive decay inside it has not yet had time to escape. Big enough that the mantle is still soft enough to convect. Big enough that the plates are still moving. Big enough that the volcanoes are still erupting, and the oceans are still being subducted, and new crust is still being made, and the whole extraordinary cycling system is still running. Size saved us. A slightly smaller planet, and the interior might have cooled enough to freeze the plates in place billions of years ago, the way Mars froze. The atmosphere might have thinned. The magnetic field might have weakened and then disappeared. The solar wind might have slowly stripped away the water, and this planet might be a cold, dry, red-brown rock drifting around a yellow star, with no ocean and no life, and no one to notice either way. But it did not happen that way. Because of size, because of heat, because the Earth was large enough and hot enough to stay alive. And what that living Earth gave, over billions of years, is everything. The atmosphere began in volcanoes. Not all at once, not from a single eruption, but from billions of years of volcanic outgassing, the slow release of gases from the interior of the Earth as magma erupted at the surface. Water vapor, carbon dioxide, sulfur dioxide, nitrogen. These gases, released in enormous quantities over geological time, accumulated in the early atmosphere. The early atmosphere was very different from the one you are breathing now. No free oxygen, mostly nitrogen, carbon dioxide, water vapor, and trace amounts of other volcanic gases. Toxic to us, if we could somehow be transported there. But the chemistry of life works in unexpected ways. The first life on Earth, single-celled organisms that emerged perhaps 3.5 to 4 billion years ago, did not need oxygen. They were anaerobic. They metabolized in that volcanic atmosphere, in warm, shallow seas, and possibly in the deep-sea hydrothermal vent systems where the chemistry of the early ocean met the heat of the interior. The oceans themselves, the water that covers 71% of the Earth's surface, that moderates the climate, that carries heat around the planet in currents, that gave birth to all life before life came to land. That water came from volcanoes. Partly. There is some evidence that some of the Earth's water was delivered by comets and asteroids in the early solar system, but a significant portion of it was outgassed from the interior. Water vapor released in eruptions, condensing and falling as rain as the early atmosphere cooled, falling for thousands of years, filling the low points of the surface, becoming the first ocean. Volcanic eruptions made rain that became the ocean that gave birth to life. And then, over billions of years, photosynthetic life, cyanobacteria and eventually plants, began producing oxygen as a byproduct of their metabolism. Oxygen accumulated in the atmosphere, and the atmosphere shifted from a volcanic, reducing atmosphere to the oxygen-rich one we have now, the one that made complex multicellular life possible, the one that eventually made us possible. The volcanoes started the chain. Everything else followed. The minerals in the soil, the phosphorus and potassium and calcium and iron, and dozens of other elements that plants need and that you need, that end up in your food and in your bones, and in the enzymes running every chemical reaction in every cell in your body right now. Those elements were distributed across the land surface of the Earth, largely by volcanic activity. Volcanic rock weathers into extraordinarily fertile soil. The flanks of volcanoes, in regions from Italy to Indonesia to Central America, are some of the most agriculturally productive land on Earth. The populations that cluster around active volcanoes, and they do cluster there, because the soil is so good, are not being irrational. They are weighing a risk that happens rarely, on a geological timescale, against a benefit that is immediate and real, and feeding their families every year. The volcanic soil of the Campania region around Naples, the same region that has Vesuvius, grows some of the world's best tomatoes. The volcanic slopes of Etna produce wine grapes that make wines with a minerality that sommeliers describe as volcanic, an actual detectable quality in the taste of the wine that comes from the mineral composition of the lava soil the vines grow in. You can, if you pay attention, taste a volcano in a glass of Etna wine. The same soil, the same minerals, from the same eruptions. Yellowstone. It sits in the northwest corner of Wyoming, in a high plateau in the Rocky Mountains, and it is one of the most geologically extraordinary places on Earth. The famous geysers and hot springs and mud pots and fumaroles, Old Faithful erupting on its rough schedule, the grand prismatic spring with its rings of color from thermophilic bacteria living in progressively cooler water at different distances from the vent. All of it powered by one of the largest active magmatic systems on Earth. Yellowstone sits above a hotspot, similar in origin to the Hawaii hotspot, but different in character because the overlying crust is continental rather than oceanic. Continental crust is thicker, lighter, more silica-rich. When a mantle plume punches through continental crust, the resulting volcanic system tends to produce more viscous, more gas-rich, more explosive magma than a hotspot beneath oceanic crust. The Yellowstone hotspot has been active for at least 17 million years. Like the Hawaii hotspot, it has left a trail of ancient calderas across the surface as the North American plate has moved over it. This trail runs northeast from Yellowstone, across southern Idaho, as a series of ancient caldera systems now covered by sediment. Each one was the Yellowstone of its time, a massive volcanic system above the same hotspot, now moved away and extinct. The current Yellowstone caldera is the result of 3 enormous eruptions in the last 2.1 million years. 2.1 million years ago, 1.3 million years ago, 640,000 years ago. Each eruption was what geologists call a super-eruption, an eruption with a volcanic explosivity index of 8, the largest category on the scale. Each one ejected hundreds to thousands of cubic kilometers of material. Each one was far larger than Tambora, far larger than any eruption in recorded human history. The most recent Yellowstone supereruption, 640,000 years ago, ejected about 1,000 cubic kilometers of ash and rock. It covered much of western North America in ash. It would have had profound effects on the climate. It happened 640,000 years ago, long before any human being existed, and it still shaped the landscape of the continent. People sometimes ask whether Yellowstone is about to erupt again. Scientists who monitor Yellowstone, and it is monitored intensively, will say carefully that there is no evidence of an imminent supereruption, that the geodetic data, the seismic data, the measurements of gas emissions do not suggest unusual activity beyond the system's normal level of restlessness. But Yellowstone is restless. The ground above the magma chamber inflates and deflates by centimeters every year as magma and hydrothermal fluids move below. Earthquake swarms occur regularly, hundreds of small earthquakes over a few days, as the brittle rock at the edges of the system adjusts to the stress. It is not quiet. It is breathing. The Yellowstone magma chamber, or more accurately, the interconnected series of magma bodies beneath the caldera, contains partially molten rock. Not fully molten. The system is maybe 5 to 15% melt in the upper chamber, which is actually relatively low. For a volcanic eruption to occur, the melt fraction generally needs to be much higher, and the pressure needs to increase significantly. Neither of those things is happening on any alarming timescale right now. What Yellowstone does do, continuously, is release heat. The hydrothermal system at Yellowstone releases more heat than any other hydrothermal system in the world that is not directly associated with an active eruption. Around 6,000 megawatts of heat, flowing continuously from the magma body below, through the rock and water above, and into the atmosphere. 6,000 megawatts, enough to power several cities, just quietly releasing heat. As it has done for 640,000 years since the last supereruption. As it will do for however long it takes until the next one. The geysers are the most visible expression of that heat. The groundwater percolates down through the rock, gets heated by the hydrothermal system, builds up pressure in underground chambers and constrictions, and then erupts upward as steam and hot water. Old Faithful erupts roughly every 90 minutes, give or take. the timing depending on the duration and size of the previous eruption. It has been doing this reliably enough to be called faithful since at least the time European explorers first documented it in the 1870s. Probably much longer. The geysers of Yellowstone are, in their own quiet way, another version of the same story. Heat from below, finding a way to the surface. Not as lava, as water. Steam. A column of hot water rising 50 meters into the cold Wyoming air and then falling back, and the underground chamber refilling, and the process beginning again. It is the same impulse as a volcanic eruption, just smaller, just gentler. Just the earth exhaling in a way that tourists can stand close to without being in danger. Right now, tonight, as you lie there, Old Faithful has erupted in the last 90 minutes. Or will erupt in the next 90 minutes. One of those is certainly true. The same water that has been cycling through that system for years, decades, is moving through the hot rock below the geyser basin, heating up, building pressure, finding the same path to the surface it has always found. Tonight. Right now, in the dark of Wyoming. There are around 20 volcanoes erupting at this moment on Earth. That number is roughly consistent year over year. It is not a sign of unusual activity. It is just the planet operating normally, releasing heat, cycling material, doing what it has always done. Kilauea is probably among them. It has been erupting, or on the edge of erupting, for most of the last 4 decades. Etna is very likely among them. Etna erupts so frequently that it would be unusual for it not to be active. Stromboli is absolutely among them, as it has been for 2,000 years, its summit flickering every 20 minutes or so, patient as the sea around it. There are volcanoes in Papua New Guinea erupting tonight. Volcanoes in Vanuatu. Volcanoes in Kamchatka, in the Russian Far East, a peninsula so remote and so volcanically active that it has over 160 volcanoes, 29 of them considered active, many of them in a state of continuous or near-continuous eruption, sending ash columns into the sky above the North Pacific, with almost no one watching except satellites. In the Afar Triangle in Ethiopia, where 3 tectonic plates are pulling apart from each other, the ground is being stretched thin, the mantle is welling up from below, and the landscape is one of the most geologically active on Earth. The Erta Ale volcano in the Afar has maintained a lava lake in its summit crater almost continuously for over 50 years. A lake of molten rock, quietly bubbling and circulating in a crater in one of the most remote and inhospitable places on the surface of the Earth. The lava lake rises and falls. The crust on its surface breaks and heals. The convection of the magma creates slow patterns on the surface of the lake, like a living thing thinking slowly. Nobody is watching it tonight. No tourists, almost certainly. The Afar is not a comfortable place. But it is there. The lake is there, moving in the dark. And under the oceans, which cover most of the planet's surface, the volcanic activity that happens at mid-ocean ridges is essentially continuous. New crust being made every day along the 65,000-kilometer global system of mid-ocean ridges. Lava erupting onto the ocean floor in total darkness under kilometers of water. The eruptions detected only by hydrophones and occasional robotic submarine visits. The new rock cooling instantly in the cold seawater and forming pillow lavas that pile up year after year, decade after decade, century after century, building the ocean floor outward from the ridge, carrying the record of the Earth's magnetic field reversals in the striped patterns of magnetization in the basalt, each stripe a chapter in the history of the Earth's interior. The ocean floor is a library, Every stripe of magnetic basalt is a record of what the core was doing when that rock solidified. And it has been written continuously for hundreds of millions of years, spreading outward from the ridges in both directions. We have read parts of it, enough to understand the broad history of how the ocean basins opened and widened over geological time. Not all of it. The library is vast, and most of it is unread, and most of it is under several kilometers of water in darkness. But it is there. All of it is there. The heat that made it is still making more of it right now, tonight, at the bottom of the Atlantic and the Pacific and the Indian Ocean and the Arctic Ocean, in darkness and silence. New rock forming at temperatures of 1,200 degrees Celsius and cooling in water at 2 degrees Celsius. The most extreme thermal gradient on the surface of the Earth, happening in total darkness with no witness. And you are here. On the surface, in the warmth, breathing. The thin shell of rock between you and all of that is holding, as it has held for the entire history of your species, and for billions of years before that, patiently, stably, doing its job without any effort, because it is not trying to do anything. It just is. Rock. Ancient, cooled, settled rock that was magma once and will be magma again in some unimaginable future when the plate it is riding on eventually reaches a subduction zone and descends back into the mantle, rejoining the cycle. Your floor has a future as well as a past. Both of them involve fire in the longest view. And yet here, in the middle of the story, it is just floor. Just solid, reliable, ordinary floor. And it will be floor for longer than you need it to be. Longer than your grandchildren will need it to be. Longer than anyone you can imagine needing it. The fire is there, but it is far away. And between you and it is more rock than you can really picture. Layered and dense and ancient, holding the heat below where it belongs, letting only a tiny fraction of it escape slowly through the surface, warming the ground by barely a measurable amount, not enough to feel, not enough to matter. Just enough to drive everything. The 20 or so volcanoes erupting right now are doing what they have always done. Building land, releasing heat, cycling material, making new rock from old, sending their gases into the atmosphere, adding trace amounts of sulfur and carbon and water vapor to the air. Processes that, over geological time, have maintained the balance of the atmosphere, the balance of the carbon cycle, the long, slow regulation of the planet's temperature. Volcanoes are part of the thermostat. When the Earth gets too cold, ice ages expand the ice sheets, the oceans cool, the weathering of silicate rocks on land slows down, which means less carbon dioxide is being drawn out of the atmosphere by that weathering, and the volcanic outgassing of carbon dioxide gradually accumulates in the atmosphere, warming the planet back up. When the Earth gets too warm, increased weathering draws more carbon dioxide down. Volcanic outgassing does not change much, and the atmospheric carbon dioxide concentration slowly falls, cooling things. It is a slow thermostat. It operates on timescales of millions of years. But it has kept the Earth within a habitable range of temperatures for billions of years, through ice ages and warm periods, through the rise and fall of continents and ocean basins, through every mass extinction and recovery. The volcanoes are part of why this planet is still habitable, still here, still able to have oceans and weather and seasons and life, still able to have you, lying there, listening. The magma below Yellowstone and below Kilauea and below Vesuvius and below every other volcanic system on Earth is just the Earth's interior reaching toward the surface. Heat looking for a way out. Not hostile, not purposeful, just physical. Just the inevitable consequence of having a planet-sized object full of ancient heat and nowhere for it to go except slowly, slowly outward. And the surface, this cool, thin shell where everything lives, where the oceans sit and the weather moves and the forests grow and the cities rise, is just the place where that heat has escaped long enough to cool down. A temporary arrangement of cooled rock sitting on top of something that never fully cools, never fully settles, never stops. The plates will keep moving. The volcanoes will keep erupting. New islands will form, and old ones will erode back into the sea. Mountain ranges will rise and be worn flat by rain. Ocean basins will open and close, and through all of it, the fire at the center will keep burning. Slowly, patiently, without urgency, without awareness, without any quality we could recognize as intention. Just heat. Just the oldest heat in the solar system, still here, still moving outward, one slow degree at a time. Still there, somewhere below you right now, the temperature is increasing. A few kilometers down, already warmer than the surface. Deeper, warmer still. And at the very bottom of the mantle, at the core mantle boundary, the temperature jumps dramatically, from mantle temperatures to core temperatures, a thermal boundary layer where the solid silicate mantle meets the liquid iron outer core, a place of enormous heat flux, a place where the dynamics of the entire planet converge. And at the center, that iron ball, spinning slowly inside the liquid outer core, at the temperature of the surface of the sun, in total silence, in total darkness, unchanged, as it has been since before the moon formed, since before the Earth had an ocean, since before anything we would recognize as Earth existed. The same heat, still there, still slowly, slowly moving outward. Through 6,000 kilometers of rock and iron, through the mantle, through the crust, through the floor beneath you, out into the night air, dispersing. The tiniest fraction of the heat of the beginning of the solar system, finding its way out through the rock and into the dark. Still moving, still there, still. Good night.